Hello everyone, my name is Naina and I'm from the Beauty Academy. So today we'll continue with the part hydrocarbons. In our last video we have seen about alkenes. Now in today's video we will basically learn about alkenes. These are the molecules with double bonds. Now alkenes are unsaturated hydrocarbons containing at least one double bond. Now alkenes are saturated hydrocarbons with single bonds, whereas alkenes and alkynes are the unsaturated hydrocarbons containing double and triple bonds. Now here we will be learning about alkenes, okay, which at least contain one double bond in them. Now if there is one double bond between two carbon atoms in alkenes, they must possess two hydrogen atoms less than alkenes. Now whenever you have alkenes, okay, whenever you have a double bond present between two carbon atoms, initially when there was single bond between carbon atoms, they each had 3 hydrogens because carbon has a tetravalency. Now if you have a double bond between carbon atoms, each carbon atom will have 2 hydrogens each. So it is 2 less hydrogens than your simple single bond carbon alkenes. Okay, so this is your alkene and this is your alkenes. Now hence general formula for alkenes is, so the general formula for alkenes is CnH2n. CnH2n. But for alkenes we used to write something called as +1 here, right? But for alkenes we don't write this +1. It is CnH2n only. Okay, so this is the general formula for alkenes. Now alkenes are also known as olefins or oil forming, since the first member ethylene or ethene was found to form an oily liquid on reaction with chlorine. So alkenes, they are also known as olefins or oil forming compounds because the first member, okay, the first member of alkenes is your ethene or ethylene. Okay, now this ethene when reacted with chlorine forms a oily liquid. Okay, because of this the ethene molecules are said to be olefins or oil forming molecules. Now the structure of double bond. Carbon-carbon double bond in alkenes consists of one strong sigma bond. Enthalpy will be 397. Now due to head-on overlapping of sp2 hybridized orbitals and one weak pi bond, okay, obtained by lateral or sideways overlapping of the 2p orbitals of the two carbon atoms. Now when you have a sigma bond, this is your p bond of carbon and this is your s bond of hydrogen, or your sigma bonds, okay, they are formed by head-on overlapping. Now this is the sp2 hybridized ka carbon bond, again this is another sp2 hybridized carbon. Now both of the sp2 hybridized carbons are overlapping head-on with each other. This forms a sigma bond. Now whereas your pi bonds, okay, now pi bond is formed like this. They are laterally paired. Okay, so this is your pi bond formation. So this is the weakest bond and this is the strongest bond. Okay, sigma is the strongest bond and pi bond is the weakest bond. Now the double bond is shorter in bond length than the CC single bond. Now you have already read that the pi bond is weaker bond due to poor sideways overlapping between the 2p orbitals. Now in our previous chapters also we have seen about the pi bond formation, which is laterally formed, and because of this lateral overlapping the pi bond is considered to be weak. Thus, the presence of pi bond makes alkenes behave as a source of loosely held mobile electrons. So, because of this weak pi bonds, okay, alkene molecules have loosely held electrons, mobile electrons in them, because the moment any reagent comes, the pi bond will break and it will make sure that each of those reagents get a electron. So, pi bond is considered to be behave like a source of loosely held mobile electrons. Now therefore alkenes are easily attacked by reagents or compounds which are in search of electrons. Okay, so hence because of this pi bond, alkenes are considered to be highly reactive, okay, because or easily attacked by any reagent or compound because they will easily lose up the electrons which are associated with the pi bonds. Now such reagents are called electrophilic reagents. Okay, now those are called as electrophilic reagents. Now the presence of weaker pi bond makes alkenes unstable molecules in comparison to alkenes, and thus alkenes can be changed into single bond compounds by combining with the electrophilic reagent. Okay, now what electrophilic reagents are? Electrophilic reagents are electron deficient reagents. So if those electrophilic reagents that are electron deficient reagents, when we add them into alkenes, they will directly go and attack the pi bonds and they will try to obtain the electrons which are associated with the pi bonds. Okay, so in this case alkenes are considered to be unstable than alkanes, because alkanes only have single bonds and they are tightly held, whereas alkene has a pi bond which is loosely held, and it makes sure that for electrophilic reagents or electron deficient reagents which are there, they can obtain those electrons from alkenes. That's why alkenes are considered to be unstable compared to alkanes. Now alkenes, because of this, they can be changed into single bond compounds by combining with the electrophilic reagents. Okay, now strength of the double bond or bond enthalpy is greater than that of a carbon-carbon single bond in ethane. Okay, so the enthalpy, the removal or the bond enthalpy, the energy that is required to break the bond, okay, is greater than that of the carbon-carbon single bond in ethane. Okay, now strength of the double bonds is greater than the carbon-carbon single bond in ethane. Now orbital diagrams for ethene molecule. Now this is the orbital diagram for ethene molecule. Now orbital picture of ethene depicting sigma bond only. So here they have only depicted the sigma bond, no pi bonds are shown. Now nomenclature. For nomenclature, alkenes in IUPAC system, the longest chain of carbon atom containing the double bond is selected. So as usual, you have to select the longest chain, but this chain should contain the double bond, okay, at least one double bond. The numbering of the chain is done from the end which is nearer to the double bond. Okay, so you have to make sure that the lowest possible number should be given to the carbon containing the double bond. Now for alkanes, every name ended with ANE, right? Now for alkenes, every name will end with ENE. Okay, the suffix will be ENE, which replaces your ANE from alkenes. It may be remembered that the first member of alkene series is CH2, replacing N by 1 in C2H2N, known as methene, but has a very short life. So the first group is your methene, but methene molecule, it doesn't exist, it has a short life. Okay, so as already mentioned, the first stable member of alkenes is your C2H4, that is your ethylene or ethene. Ethylene is the common name and ethene is your IUPAC name. Okay, now some of the structures and their IUPAC names are given here. So this is propene, this is but1ene, but2ene, but1,2,1,3-diene, because you have two double bonds. Now 2-methyl prop1ene. On second carbon you have your methyl group, and on first carbon you have your double bond. So it is 2-methyl prop1ene. Okay, so on. Now next is the isomerism. Okay, now alkenes show structural isomerism and geometrical isomerism. Now alkenes, they show two types of isomerism, structural and geometrical. Now structural isomerism, as in alkenes, ethene and propene can have only one structure, but alkenes higher than propene have different structures. So structural isomerism for ethene and propene, it will have only one structure, but after propene, the higher alkenes will have different structures. From butene, there have many structures. Now, alkene possessing C4H8 has a molecular formula, can be written in the following ways. Okay, so there are three ways in which you can write your butene. So this is but1ene, your normal structure. Then you have but2ene. Okay, this is the second one, and the third one is your 2-methyl prop-1-ene. Now, these are structural isomers. Okay, even though they have same chemical formula, that is C4H8, but it can form 3 different structure. Okay, now the structures 1 and 3 and 2 and 3 are the examples of chain isomerism. Now, these are the examples of chain isomerism 1 and 3, 2 and 3. Okay, chain isomerism, whereas 1 and 2 are position isomerisms. Okay, since these are chain isomerism, 1 and 2 are position isomerism. Why position isomerism? Here the double bond is associated with your first carbon, whereas here the double bond is associated with your second carbon. So the position is changing for the double bond, hence it is your position isomerism. Okay, now next one is your geometrical isomerism. Now doubly bonded carbon atoms have to satisfy the remaining 2 valencies by joining with 2 atoms or groups. Okay, so the doubly bonded carbon atoms, to satisfy the remaining 2 valencies, they have to join 2 atoms or groups. Okay, because once your carbon-carbon double bond is there, since carbon is tetravalent, so it has to fulfill 2 more valencies. So to fulfill these 2 more valencies, they can either join 2 atoms or groups. Okay, now if 2 atoms or groups attached to each carbon atom are different, they can be represented as YXC double bond CXY, like structures. Okay, so you can have, if your carbon-carbon double bond is attached to 2 different molecules, okay, YX, XY, okay, XY, XY, then you have here both the X's are on same side and both the Y's are on same side. Here they are oppositely placed. Okay, now in A, where both the X's are on same side, okay, where both the X's are on same side, the 2 identical atoms, that is both X or both Y, lie on the same side of the double bond. But in B, what happens? They are present cross to each other, right? Okay, they are present cross to each other. Now, this results in the different geometry. You can get 2 different type of geometry where both the molecules are present on the same side, and in the second structure they are present opposite to each other. Now, disposition of atoms or groups in space in the 2 arrangement is different. Now, therefore, they are stereoisomers. So, these are called as stereoisomers. Okay. Now, they have this same geometry if atom or groups around C double bond C, that is carbon double bond carbon, can be rotated, but rotation around them is not free. Okay, it is restricted, because whenever they rotate, there is some kind of energy that is required. Okay, now for understanding this concept, take 2 pieces of strong cardboards and join them with help of 2 nails. Now hold one cardboard in your one hand and try to rotate the other. Okay, the answer is no. So whenever you take 2 cardboards, nail them together and try to rotate them. Will it rotate? No, it will be difficult to rotate them because you have nailed and fixed it, right? Now the rotation is restricted. Now this illustrates that the restricted rotation of atoms or groups around a doubly bonded carbon atom gives rise to different geometries of such compounds. So whenever you forcefully rotate them, they require more and more energy. Okay, this restricted rotation of atoms or group of around the doubly bonded carbon, they give rise to different geometries. Okay, now the stereoisomers of this type are called geometrical isomers. Okay, now they are called as geometrical isomers. Now the isomer of the type A, in which 2 identical atoms or groups lie on the same side of the double bond, is called cis-isomer. Okay, when you have molecule, when both the molecules are present on the same side of the carbon-carbon double bond, okay, these are called as cis isomers when they are present opposite to each other. Okay, when they are present opposite to each other, they are called as trans isomers. Okay, now thus cis and trans isomers have the same structure but have different configuration or arrangement of the atom or group in the space. Okay, now here these molecules have same formula, okay, same structure, but the same formula and same structure, but the arrangement will be different in the space. Once it can be on same side or it can be on opposite side. Now this is trans. Okay, now due to the different arrangement of atoms or groups in space, these isomers differ in their properties like melting point, boiling point, dipole moment, solubility, etc. So because of their difference in spatial arrangement, they can have different properties like melting point. The melting point, boiling point, dipole movement, solubility can change. Okay, now geometrical or cis-trans isomers of butene is represented here. Now this is an example, butene. Now this is your cis-butene because both methyl groups are and hydrogens are on the same sides. Now here they are on the opposite side. So this is trans-butene. Now cis form of alkenes is found to be more polar than the trans form. Okay. Now cis form is found to be more polar than your trans form. For example, dipole moment of cis-butene is 0.33 dB, whereas dipole moment of trans form is almost 0. Okay. It can be said that trans-butene is non-polar. This can be understood by drawing geometries of the two forms of as given below. Now you can get a question when they will ask you why the cis-butene is polar whereas trans-butene is non-polar. Then the answer lies here. Now this can be understood by drawing the geometries of the two forms. Okay. Now here you can see this is the cis form where both the dipole moment is towards the double bond. Okay, so you can get a net polarity, whereas for trans you can see both the polarities are toward the opposite direction. So these two can cancel out and you can get a zero value. Now this is the reason why cis butene is considered to be polar whereas trans butene is considered to be non-polar. Okay, in the case of solids it is observed that the trans isomer has higher melting point than cis form. Okay, whenever the molecules are present in solid, it is considered that trans isomers, okay, they are having higher melting point than your cis. Now geometrical or cis-trans isomers is also shown by alkenes of the types where you have different molecules altogetherly attached. Okay, next is the preparations of alkenes. Now you can prepare alkenes from your alkynes. Now alkynes on partial reduction with calculated amount of dihydrogen in the presence of palladized charcoal partially deactivated with poisons like sulfur compounds or quinoline give alkenes. So whenever you reduce your alkyne, okay, when you reduce your alkyne with sufficient amount of dihydrogen in presence of palladized charcoal, okay, which is partially deactivated with your sulfur compounds or quinoline, gives you alkene. Okay, now partially deactivated palladized charcoal is known as Lindar's catalyst. Okay, when you have a partially deactivated palladized charcoal, you call it as Lindar's catalyst. Now alkenes thus obtained are having cis geometry. So the alkenes which are obtained from alkynes using Lindar's catalyst has a cis geometry. Okay, now however alkynes on reduction with sodium in liquid ammonia forms trans alkenes. Okay, so if you want trans alkenes from your alkynes, then you have to reduce it using sodium liquid in ammonia. Okay, sodium in liquid ammonia. So when you have alkynes which you react with dihydrogen in the presence of Lindar's catalyst, you get cis alkenes, whereas when you react alkynes with hydrogen in the presence of sodium in liquid ammonia, you get a trans alkene. Okay, now these are the examples. Now, from alkyl halides. Okay, first we have seen from alkynes. Now from alkyl halides. Alkyl halides means your Rx. Now your X can be Cl, Br, I, anything. Now alkyl halides, when you heat them with alcoholic potash. Alcoholic potash means potassium hydroxide dissolved in alcohol, say ethanol. Okay, alcoholic potash means you have take potassium hydroxide and dissolve it in alcohol, same ethanol or methanol. Okay, now eliminate one molecule of halogen acid to form alkenes. Now in this process what happens, your Rx, okay, when you react it with potash alcohol, okay, alcoholic potash, it removes the halogen, okay, and it converts that into a double bond. Now this reaction is known as dehydrohalogenation. Okay, so this reaction where you use alkyl halides to form your alkenes are called as dehydrohalogenation, because you are removing one halogen, that is removal of halogen acid. Okay, that means you remove it using HCl, HBr or HI. This is how your aldehyde halides are removed. That's why it is dehydrohalogenation. Now this is the example of beta elimination reaction. Okay, since hydrogen atom is eliminated from beta carbon atom, now carbon atom next to the carbon to which halogen is attached. Now this is called as beta elimination reaction. Why? I'll tell you. You have C double okay, you have an halogen. Here you have considered this to be chloroethane. Okay, this is your chloroethane. So whenever you remove this chlorine, it is removed along with the hydrogen which is present on the adjacent carbon. Now this adjacent carbon is called as beta carbon, which is attached to your alpha halogen. Okay, now once you remove this, what will happen? There will be electrons left on both the carbons. They come together and form your alkenes. Okay, now nature of halogen atom and alkyl group determine the rate of reaction. Now which type of halogen is present, whether it is chloroethane, bromoethane or iodoethane, and the nature of the halogen atom and the alkyl group will determine the rate of reaction. Now it is observed that the rate of reaction, when according to the halogens present, iodine is more reactive than bromine than chlorine, while for alkyl groups, tertiary alkyl group is more reactive than secondary than primary. So these two you have to remember. Now next, from the vicinal dihalides. Vicinal dihalides means when you have halides on both the carbon atoms. Okay, in this case what will happen is dihalides which two halogens atoms are attached to two adjacent carbon atoms are known as vicinal dihalides, as I showed you here. Now vicinal dihalides on treatment with zinc metal lose a molecule of ZnX2. Now when you have vicinal dihalides, you have to react it with Zn. Okay, when you react it with Zn, these two halogens are taken up by Zn and the double bond is formed here. Okay, this is called as dehalogenation. Second one is your next one is from alcohols by acidic dehydration. Okay, now you have read during nomenclature of different homologous series that alcohols are the hydroxy derivatives of alkanes. You add OH to your alkanes, you get alcohols, right? Now, they represented the ROH group, where R can be your alkanes. Now alcohols on heating with concentrated sulfuric acid forms alkenes. So whenever you have alcohol, when you heat it with concentrated sulfuric acid, it forms your alkenes. Okay, which eliminates one water molecule. Now since A water molecule is eliminated from alcohol molecule in the presence of acid. The reaction is known as acidic dehydration of alcohols. Since water molecule is removed, so it is called as acidic dehydration of alcohols because you are using acid. It is also a beta elimination since your OH group leaves with the hydrogen which is present on the adjacent carbon. Okay, so this OH group, it takes up this hydrogen and it leaves it as H2O. Okay, and you forms your alkenes. Okay, so this is the reactions of your alkenes. Next we will do the properties in our later videos. So thank you for watching my video. Please do like, share and subscribe to our channel.